Hello everyone, I am Alok Kumar and I welcome you to this third lecture on matrices and determinants. We already have covered the algebra of matrices and also inverse, and now I'll just go deeper into the subject. So let me now share my screen with you all and start the lecture. So let me just go through. Okay, so here we go. So last time we already have seen how to find inverse, or rather how to use the ideas of inverse in problem solving. And most importantly, we have also done some kind of orthogonal matrices. Today, let me start with a problem that came in JE Advanced, but I have changed it just a bit. So suppose you have got a matrix P is root 3 over 2 and 1 over 2, negative 1 over 2 and root 3 over 2, and this is a matrix P, and you define a new matrix Q as PAP transpose, where A, of course, has to be defined because A finds mention in Q, and A is 1, 1, and 0, 1. That's your matrix A. And then your job is to find out this some power they have to find. So you have to find P transpose Q to the power 2020 and times P. So you have to find this product of matrices. So let me show you the question once again, that the matrix P has these kind of elements that you can see. They of course remind you of some cos and sine business, which is good. And Q is PAP transpose, A is 1101 row wise, and Q is PAP transpose. And our interest is to find P transpose Q to the power 2020 and multiplied with P again. So this solution will first, the motivation will be that notice that this P reminds you of some matrix, that P is orthogonal, because root 3 by 2 means what comes to mind is cos of theta. It does not matter what that theta is. So I write P is cos theta. This is cos theta. I also write this is cos theta. This has sine theta, and this has negative sine theta. So that's your theta. For example, here theta is, this is 30. So theta I can 6 as pi by 6. So cos 30 I can write. This is pi by 6. This is entirely immaterial. So there is some theta. Once you say P is this, we discussed last time that this matrix is orthogonal. You must be able to easily identify these in exam, so you don't lose any time. The moment this is given to you, the first thing that should come to your mind that, oh, I know this matrix, this is some kind of a good one, and immediately your mind will give you the convincing reasoning that, oh, it's a orthogonal matrix. So it means, or it is orthogonal matrix, so we know that P inverse is nothing but P transpose. To remind you, P transpose P equal to I was the definition of orthogonal matrix, that if there is a matrix P such that P transpose P equals I, then P is orthogonal. Of course, here we can multiply and we can find it is orthogonal. And then as a bonus, you get that if P is orthogonal, then its inverse is damn easy. It's just P transpose. Clearly P transpose, and so P inverse is P transpose. Armed with this one, let me simplify Q a bit. So Q is given to be PAP transpose. PAP transpose. I want to write 1P I will retain, and P transpose I replace with P inverse. So Q is PAP inverse. Now I want to find the other thing. Like say, what is, I want to take out A. So what I will do, that I will multiply this P by P inverse and P. So pre-multiplying with P inverse and post-multiplying with P, of course, on the both sides. So that's P inverse, PAP inverse, n times P. And we can associate in any manner we want. And that association, of course, will give you that this P inverse P is again I, quickly you get, and this is PA times P inverse P. So it's like I, A, and I. This all is automatic. You can quickly write A in the exam, that is A. So now this is A. Now one more thing, which is the work I do here. If you have got that x equal to x equal to p inverse yp. If you see this kind of structure, or x equal to py p inverse, they are both same, because if I write this p inverse as say m, then this is again m inverse ym. So these two are inverses of each other. So the matrix y is sandwiched between a matrix p and its inverse. Wherever you write does not matter, they are both inverses of each other. So if x is like p inverse time yp, then keep in mind that power of x to the power n, just transfers to y. So that's p inverse y to the power n times p. As if p and p inverse, they stand guard, they don't come in between. This power n simply goes quite here. That's amazing. The proof is just one line. So we just see the pattern. We write x squared first. So x squared is p inverse yp whole square, and by definition this is p inverse yp, and again multiplied with itself, p inverse yp. Again we can associate. So power of association is in full display. pp inverse and time yp. So this p inverse becomes y. So p inverse y I yp, and these two y quickly combine. I does not interfere with them, and p inverse y squared p. So we get x squared is this much. If you keep continuing, of course, the formal proof means you have to use the word induction. And so if you drop that word, then you can say it's an easy induction that x to the power n is p inverse y to the power n equal to p. Of course, every pattern needs to be validated in maths. You cannot just say that this happens. And so induction is induction. You can say that this is this. So we know that if x is p inverse yp, then x to the power n is very easy, and it just transfers to n. And so this we get. Look at this one. We have got same thing here. We have got a is p inverse qp. So if I take a to the power any power, say a to the power k, I should get p inverse q to the power k n times p. Now your job is to find this one, q to the power this 220, and now you already know that p inverse is now p transpose. So I can write that it means that a to the power k is p transpose q to the power kp. The question asks you to find p transpose q to the power 2020 and multiplied with p, and that is nothing but a to the power 2020, and matrix a is given. Matrix a is given. A is 1 0 1 1. That's a good matrix. Again, we used in on one of the examples that if a is 1 0 and 1, and then even if it is a, then you know that a to the power n equals 1 0 1 and a. Here already you have got this kind of thing. So you will of course have, this is 1, so you have a to the power 2020. That number will be simply 101, and here you will have 2020. So that's your answer. So the problem looked quite demanding. It looked as if that it has got a lot of powers, the big powers, and so many strange things multiplied. But then once you understand how the problem was created, you can have really an easy way through its solution. Okay, so let's move on to our next example. It's a curious thing. So find the number of, so you're asking that find the number of ordered pairs. Find the number of ordered pairs AB. Ordered pairs AB, you know what an ordered pair is, of matrices such that AB minus BA equals I, and A and B as usual are given to be square matrices for things to be defined. Square matrices. So you can take n by n or anything. So now same order, of course, they will be. So find the number of ordered pairs of matrices AB such that A minus B equal to I. If this question is presented to you, what is your guess? Of course, the choices are there sometimes, or maybe this is a good question for integer type where you don't know what the answer is. But always think of extreme answers, that if there is no solution or there are infinitely many solutions. So you will find that there is no solution in this case. We'll prove by contradiction. We will prove by contradiction. So this is proof by contradiction. So what we'll say that, okay, let there be A and B. We claim that there are no matrices A and B, no ordered pair that satisfy this matrix equation. So let us assume, for the sake of contradiction, that no, there exist matrices, AB. This means there exist. So you see there exists an ordered pair AB such that AB minus BA equals I. You are saying, okay, this is I. Let's assume this and see what happens. If you get a contradiction, it means that, oh, it cannot be true, it must be false. So you are saying like this. Now a surprising twist comes to solution. Take trace on both sides. If you recall, trace is a linear function. So it means trace of x plus y, two matrices, is trace of x plus trace of y. And one more amazing property of trace was trace of xy is trace of yx. Means although matrix x and y need not commute in general, so xy is not yx in general, but then that does not stop from their trace being equal. That's proved. So trace of xy is trace of yx. We take trace on both sides. If we take trace on both sides, then I will get trace of AB minus BA is trace of I. Means this must happen. This implies this. So if that happens, then trace of AB minus trace of BA must be trace of I, that is n, because say I is a matrix of order n by n. Certainly it is not 0. So n greater than or equal to 2 I will take for the matrix to make sense. And so because trace of AB is trace of BA, so 0 equals 1, you hit the contradiction because n is a positive integer, in fact greater than or equal to 2 for matrix to make sense maybe. And so you will say that there are no pairs of matrix AB for which AB minus BA equal to I holds. Look how surprising the solution was. There was no trace in the question. It just said that, okay, there are some matrices, and suddenly the moment you see AB and BA, your mind thought that, okay, maybe trace of AB is trace of BA had something to do with it. And so you had the courage to apply it. And we assumed proof by contradiction. So we said that, okay, let there be matrices A and B such that AB minus BA equals I. And then we take trace on both sides. That's trace of AB minus BA is trace of I. And trace a linear function, it breaks. Trace of AB minus trace of BA equal to n. But then we are good here because trace of AB is trace of BA. So that demands 0 equals to n, which cannot happen sadly because n is given to be a positive integer. And so we have reached the desired contradiction. That tells you that there are no matrices A and B that satisfy AB minus BA equal to I. And so we are done. How about this one? This is another direction. So A is a matrix, A is a matrix, A is a n by n matrix, square matrix, such that A cube equals 0. So A cube equals 0. And you have to find out whether M matrix M given by half A square plus A plus I, and second given by n equal to half A square minus A plus I. You have to find out that whether these are invertible or not. So maybe choices can be that typical IT choices that M and N both invertible, neither M nor N is invertible, M is invertible but N is not, and fourth, N is invertible but M is not. All those are just ways of asking the multiple choice questions, but let's get to the subject. So A cube is 0 and M is this one. You want this one to be, you want to make up your mind about whether matrices M and N are invertible or they are not. So I gave you advice last time that think of some identity that reminds you that this might be a part of it. So think of some algebraic scalar identity, say in X. So half x squared plus x plus 1. Have you seen it somewhere? Is it part of some identity? Well, if you think for a moment, you will find that yes, it does. So how about this one? 1 by 4 h to the power 4 plus 1. It factorizes as half x squared plus x plus 1 n times half x squared minus x plus 1. That's plain. In fact, h to the power 4 plus 4, every high schooler is supposed to know. and you did it in your class 8 or 9, and this is just you are writing x squared plus 2 in case you have forgotten. 2 squared completely squared, 2 times x squared into 2, and then because you've given this extra, so you must subtract, that is minus 4x squared. So x squared plus 2 whole square it becomes, and minus 2x whole square, and then x squared plus 2x plus 2 a plus b, and x squared minus 2x plus 2. It's the same thing. I have taken the 4 this side, so it's like 1 by 4 x to the 4 plus 1. There is an identity called a to the power 4 plus 4 b to the power 4 that you are supposed to make note of it for your future use. So it's a squared plus 2a plus 2b squared, and a squared minus 2ab and plus 2b squared. And this is known as, this has got a name. It has got a Sophie Germain identity. It's highly recommended that you remember it. You, of course, keep it in mind. It may help you. So this is your identity. So we have just taken b equal to 1. So we have made use of this one, half x squared. I told you that any polynomial identity will remain valid if you replace x with a and 1 with I. If you replace, I'm not writing equal to, you replace x with a and 1 with I, it will still remain valid, because that a and I of course commute the way x and 1 commute here. So 1 by 4 a to the power 4 plus I, we can say that this follows that half a square plus a plus I and times half a square minus a plus I. And once that is done, we note that a cube is 0. That immediately gives you this goes to 0. And so you have I equals, this was given to be m and this was given to be n. So I equals mn. Let us write mn equal to I in this form. Now this tells you that both m and n are inverse of each other. In fact, to recall that if A is a matrix and you can find a matrix B, so given a matrix A, given A, find B, or you can find B such that BA equal to I. This is enough to guarantee, enough to conclude that B is the inverse of A. Because I told you last time that BA equal to I, of course, will imply AB equal to I. So there is no, so whatever applies with left applies with right also. And so the moment you get mn equal to I, you can say that m is inverse of n, and in the same way n is inverse of m. They are mutually reciprocating, and so we will say that both are invertible. So of course both are invertible, and in fact both are inverse of each other. So inverse of m is n and inverse of n is m. So the question answer is affirmative, that yes, they are invertible. Let's move on to a question from orthogonal matrices that says M is 3 by 3 matrix as usual, because IIT has got matrices up to order 3, it is not up to order 3, and so they would not give you 4 by 4 or something else. And one more aspect is that whatever you learn for 3 by 3, of course it applies to other thing in general, and so the testing is already completed by then. So M is 3 by 3 and det of M equal to 1, and you are given M transpose M equal to I. So did not say directly that M is orthogonal. They just wrote the definition itself. M transpose M is I. So M is orthogonal, we know now. And we want to find det of M minus I. Det of M minus I. Now, if that is the case, then let's try to find what det minus M minus I is. So we rewrite it. So we rewrite M minus I in a different form. So M minus I equals, I want to use M transpose in some way because I know that M transpose M is I. So I can write this as Mi minus this I will again write as M transpose. So it means I can take out M, and this is I minus M transpose. You can check that this again holds, M minus M transpose. So it does not take long to realize that this I transpose minus M transpose, and you are using A transpose minus B transpose. That's A minus B and whole transpose. So transpose comes out of the bracket. That's good news. So I M minus M transpose. So the thing returns, m minus I again returns, albeit with a different sign, negative sign. That really actually helps us. So now we take det on both sides. So det of m minus I is det of m in times I minus m transpose. That is det of AB is det of A. We are using again det of AB as det of A times det of B. Determinant of product is product of determinants, det of M, and times det of I minus M transpose. We also know that det of A transpose is det of A, and so det of M is all right. And this I can write det of I minus M. So this is det of M, and times det of I minus M, I can write negative of M minus I. Sorry about that. And det of Ka, if K is scalar, is nothing but K to the power n det of A, where n is the order of a square matrix A. So A is n by n. So this K times n, that is pulled out. So it's det of m n times minus 1 to the power 3, because m is given to be 3 by 3. Let me scroll. Yes, it's 3 by 3. If it was 4 by 4, you would not have any advantage. So this is determinant of m minus I. So you get negative of determinant of m, that is given to be 1. So negative, this is 1. So negative det of m minus I. And you have got the same thing on the left side. And together they add up. So 2 determinant m minus I is 0, giving you that det of m minus I indeed equals 0. Now 2 points about this question. First, it was not enough to give m is orthogonal. They needed to give determinant also, because m transpose m equal to I. If you take det on both sides, you will get det of m transpose m is det of I. And because det of m transpose is m transpose, so this further simplifies to det of m is 1, and det of m squared equals 1. And that gives you det of m could be either 1 or negative 1. So I need to be given that what det m is. So they supplied this, and det m was going to be negative 1. And then this negative was actually this way. If it was plus 1, you can't include anything. That is det of m minus I, det of m minus I. We don't know the value. So this is a good question based on this. Let me generalize this in some way. So the generalization will look like this, that now instead of one matrix, there are two matrices now. So A and B of 3 by 3 matrices, square matrices, orthogonal. So they are both orthogonal. And det of A plus det of B equals 0. And I want to find det of A plus B. Det of A plus B. You know, there is no rule like det of A plus B. Although you could be forgiven for thinking that det of A plus B is det of A plus det of B, which is wrong. But it gives the correct answer here. But of course it is wrong. So be warned. Now det of A plus B, A and B is orthogonal. So how do you start that? Taking your motivation from the last problem. So last problem was that crucially m minus m I was able to write in terms of, so let us scroll, m minus m I was able to write ultimately on which the problem was riding is m minus y is m times I minus m transpose. So I'm able to write m minus I equals, so I'm able to write this as m times I minus m transpose. That is what made it work. Let's derive something similar for, say, this example, that is A plus B. That what A plus B I can write. I will prove that A plus B, and this you should note for future use again. These are real small gems which you must keep in mind if you want to do well. And I of course know I want to do well if you're watching the video. So A plus B is A times A inverse plus B inverse n times B. So this I am proving for matrices in which A and B are invertible. A and B are invertible. Right now, I'm nothing about orthogonality. M is A and B are invertible. Then we will get A plus B is A inverse plus B inverse times B. That we can quickly, of course, verify. But we can write also in this way that a plus b I will write as a times I and plus I times b. Notice how I am writing ai and ib for purposes that will become clear. So a times, and this I can write as b inverse b, because this is this way b, and this I will write as a inverse b. Notice how a is here and a is here, and here you have got b, and here also you have got b. These two, they're in the same position, same corresponding position. That is very important if you want to take something common, because this matrix multiplicity is not commutative. So if I take a and b out, so I can write a times b inverse plus a inverse and b. And please double check, means go back from this to this. Yes, it does match that a b inverse b, so you are getting, and this a inverse b, so ai plus b. So we got this finally, means we got that for any two invertible matrices of the same order, a plus b equals a times, I can write a inverse plus b inverse and times b. This I can write this one. This is for any two matrices a and b of same order and orthogonal. Now, if a is it is for invertible in fact. So, but if it is orthogonal, if a and b are orthogonal, then we can make use of in good way. If a b are orthogonal, then you know that a inverse is a transpose and b inverse is b transpose. So I can rewrite this as a plus b equals a times a transpose plus b transpose times b, and that's a times, again this transpose comes out of the bracket, a plus b transpose. Remember, x plus y transpose, the law is x transpose plus y transpose. We are applying not this direction, but apply this direction. Both are equivalent. You must be able to switch between two sides. That's one of the skills you must develop. Now a plus b transpose. So now what I can do, that remember how good it was. There is no formula as such that a inverse plus b inverse, it does not come out. There is nothing like this. There is nothing like this. So you will remember that, okay, nothing like this. That's why transpose is needed badly to take something out. Now a plus b, so we got a plus b, that is we got a plus b is a times a plus b transpose b. Now things look really good and we are ready to take determinant. So let's take det of a plus b and apply the same steps, that det of a times a plus b transpose and b, use a big bracket. So that's det of a times det of a plus b transpose and times det of b. Now, because det of a plus det of b is 0, you know orthogonal matrix, it means det of a is 1 or minus 1, and similarly det of b also is 1 or minus 1. It is given sum is 0, so one of them is 1, other is negative 1. Which one is 1? I don't care. We did not need. So det of a and det of b, so det of a and times det of b here, and this number is nothing but same det of a plus b only, because det of x transpose is det of x. So now we are getting this negative 1 and times det of a plus b. You bring this side, and so 2 times det of a plus b is 0. That is again giving you det of a plus b equals 0. So this kind of thing we will get. So these two examples are closely related, and so you should try to master them in one attempt. And please remember the identities that really are hiding behind them. One is this, a plus b, and other was, if I may scroll, other was this one. M minus I is M I minus M transpose. I'm able to write like this. This was another one. Okay. There is one problem which talks about taking powers again, that A is a matrix 3 by 3 and B also 3 by 3, both invertible given, both invertible, and B is not I, B is not identity, and A inverse is B squared, and a to the power 5 equals I, and I want to find the least positive. So find the least positive integer. The question says find the least positive find the least positive integer such that b to the power k equals I. Least positive integer k such that b to the power k equals I. A to the power 5 is given to be I, and you want to find this one now. This we can do like this. So A inverse is b squared. Now, just we discussed something like that. If you have got p x p inverse, and if you take a square of it, then a square of force transfers here. So that becomes px squared p inverse. Okay, so we can do that. So A inverse. So if I take A inverse square, let's see how it changes. A inverse squared. That becomes A and then B square and again A inverse. But B square is given to be A inverse. So I can plug it back. So B square is A inverse and again A inverse. Associate in the manner A, B, and A inverse, A square, B, A minus 2. See how easily using law of association we are associating the way we please. So that is A squared. So from this step, there is some improvement. Powers of A are rising now. This is just one power. Now A squared is there. If we continue further, A inverse and fourth power, if I write fourth power squared, this one fourth power, this one, that is A squared, B, A minus 2, and that is square of that. Again, A squared will be A square only. This is A square. You have got B square and A to the power minus 2 because they are just inverse of each other. So A square and B square, again I can write A inverse because that's given minus 2. Again, combine, so associate, that is A cube and B A to the power minus 3. So let's see how our entry is there. AB inverse squared, that happens to be A square, B A minus 2. AB A inverse 4, that happens to be A cube, B A minus 3. If I go AB A inverse and 8, not 6, because I from here to here I reached by squaring. Here to the root was by squaring. So if I square it, I will get 8. So this 8, I'll get A4, B, A minus 4, and A inverse. If I go 16, 2, 4, 8, 16, I'll end up with A5, B, A minus 5. I did not go further because my quest ends that A to the power 5, my search ends, A to the power 5 equals I. So I know that this is the right step, this is the right place to stop now. In general, we will have, if you're interested, it will be A inverse and say 2 to the power some n. So that will give you, where n is a positive integer, suppose, is A to the power n plus 1, B times A to the power minus n plus 1. For the matrix defined like in the question, that A inverse is B squared. So we will get this kind of thing, A n minus 1. Now, the moment we got this one 16, so A inverse is now B squared. So I use this here and write B to the power 32 is A5, B A minus 5. A5 is I, this is I, B, this is also I only. And so this is B. So we get B32 equals B. Because B is invertible, I can multiply B inverse both sides. So B inverse B32 equals B inverse B, or say cancellation law. So that is B to the power 31 equals I. So we get B to the power 31 equals I. Now I want the least positive integer k such that this happens. B to the power k is I. Now, because you got already this one, so the any integer k greater than I, if k is less than 31, if k is less than equal to 31, then k must divide 31. If this happens, given this. So now if this is the case, then k equal to 1 or 31. But k equal to 1 means b equal to I. But it is given that b is not I. The question precludes that. It says that b cannot be I. It's not. It's different from unit matrix. And so you will say that it means that you cannot bring it further. And so B31 must equal I. And then we can say that, okay, the least positive integer k is 31, because anyway, if I again square it, B62 also will give you I, but that will be more than 31. So 31 is the least positive integer for which b to the power k equals I. That's a good problem, depending on the properties of squaring and then inverse and other ideas also thrown in. Next, let me do a simultaneous matrix equation. So we'll call it simultaneous matrix equation. It is simultaneous matrix equation. So just like you have been given that A plus B equal to 2B transpose and 3A plus 2B equals I. You have done something called linear equations, that x plus y equal to 11 and 2x minus y equal to 13, and solve for x and y. We have also done some functional equation. I will relate to it further. So first of all, the method would be here that A occurs, you see that B has with B transpose, but then A does not have A transpose. That I will say that eliminate. So method should be that eliminate A. You can let B also, but A is better. Eliminate A between these two. So if you eliminate A, means just you will multiply the first one by 3. So that's 3 times 2B transpose. So 3 times A plus B. Multiply this by 3 and subtract. 3 times A plus B minus 3A minus 2B. That equals 6B transpose and minus I. That gives you that 3A cancels. So that gives you B equal to 6B transpose. 6B transpose minus I. So that is your B. I can rewrite on left side, B minus 6B transpose is minus I. I would like to make a comparison. When you see in complex number something AG plus, say, AG plus B G bar is equal to something alpha, then what comes to your mind? That you can create one more equation by taking conjugates. Means you can take AG plus BG bar conjugate is alpha conjugate, and so this is A conjugate G conjugate plus B conjugate and G, and that's alpha bar. And depending on A and B given real, we can further simplify that. So the whole point is that you can create a new equation using one other equation by taking some operation like conjugate here. Compare with functional equation. In function, we have f of x 2fx plus 3 times f of 1 minus x is something, say 2x plus 3, or gx, any function. If you change x to 1 minus x, what would it does? It gives you f of 1 minus x and 3 times f of x, and this is 2 times 1 minus x plus 3, or say in general g of 1 minus x. And so we end up with simultaneous equation in f of x and f of 1 minus x. So you end up with two equations, and it's like your A and B, and you can solve for A and B. Similarly, B minus 6B equal to minus I. What I'll do, I will derive from it another equation by some operation. What comes to your mind? Should I take transpose? Yes, that's the answer. If I take transpose, B minus 6B transpose is negative I transpose. I get a different thing. The equation is different. So B transpose minus 6B is negative of I. I transpose is I. So I get this kind of thing. B transpose minus 6B is negative of I. Now my job is to just eliminate any one of them because they are equal. So I can write that B minus 6B transpose is B transpose minus 6B. That can give me your this thing, that 7B is 7B transpose. So B is B transpose. So B is symmetric. And I can put B is B transpose here. So that will give me your B plus 6B. B plus 6B is 6B transpose plus B transpose. So 7b is 7b transpose. So we can get b equals b transpose. And once I do that, say here, b equal to b transpose here in the first equation. So b minus 6b equals negative of I. So minus 5b equals negative of I. And so b equals 1/5 of I, or I over 5b. And because a plus b was this one, or 3a plus 2b was I, 3a plus 2b was I. So 3a plus 2b is I. That gives you 3a plus 2 over 5 times I is I. And so 3a is 3 over 5i. And so a also equals 1/5 of I. So a and b both are equal, which again checks out. So here we had got one equation. So we got an equation bb transpose, and we made use of it to find another equation. And that equation was all right. And so we got our answer, that a different equation. So given one, but it is used twice to create more equation. Let me now go to some geometrical transformations. So some are called transformation matrices. So we have got something called transformation matrices. That is geometrically how matrix can be used. That's an interesting topic. So first thing is that we will do what is called reflection in the x-axis. Reflection in the x-axis. So let's think that we have got one. This is x and y, usual x and y. You have got point P, x comma y, and you are reflecting it in x-axis, that's P prime, and calling the image at x prime, y prime. So P prime is the image of P. So P prime is the image of P in the x-axis. In the x-axis, or say image of P after reflection in x-axis, is the same thing. So it is image of P prime. So we know for this transformation, we know that x prime equals x and y prime equals negative y. So I can write this as 1 times x plus 0 times y, and this is 0 times x plus minus 1 times y. So I can express x prime y prime in the matrix form, that x prime y prime is a matrix n times this is xy. That matrix is 1 and negative 1 on the diagonals and 0 on the off diagonal elements. So this is this kind of matrix. This matrix, which is T, I will call that the matrix T equal to 1, this is minus 1 diagonal element, and 0. This matrix in fact, this describes, or this matrix represents reflection in the x-axis. So this represents reflection of a point in the x-axis, or say this represents reflection on the x-axis. Means if there is some point, say 4,11, and you want to find how it will transform when you reflect in the x-axis, just you write 1, 0, 0 minus 1 and multiply it with 4,11. That will give you the point which is reflected, and it got in the x-axis. So 411 transforms to this point. So it is called reflection in the x-axis. We can move on to also reflection in the y-axis in a similar way. Reflection in the y-axis. For that, we say the diagram is that, okay, we have got a point P, which is x comma y, and again usual P prime is x prime y prime. And because this is reflection of in the y-axis, so this x and y reflects in the y-axis, we have our x prime and y prime. So x prime is negative of x and y prime is y. So I write is minus 1 times x plus 0 times y and 0 times x plus 1 times y. So I can write this as x prime y prime equals negative 1 0 0 1 and xy. So the matrix T, that is negative 1 0 and 1, this matrix represents reflection in the y-axis. The way this was reflection in the x-axis, that was 1 negative 1. Now obviously they've been interchanged, so -1 goes up and -1 comes down, and so this is -1 1. So they are just changed places in the diagonal. Off diagonal are same. It is natural to proceed to reflection after this axis reflection through origin. So let's do reflection through origin. That means that you have got a matrix, you have got a point P, x comma y, and P prime is again x prime y prime. So this time we know that reflection in the origin, so x prime, so reflection through origin means that O is the midpoint of P and P prime. So x prime equals negative of x and y prime equals negative of y. I can write -1 times x plus 0 times y and 0 times x plus -1 times y. And so as we wrote previously, x prime y is -1, -1, 0, 0 here off diagonal, and this is x and y. And so the matrix T equal to -1, -1 here and 0, 0. This matrix, this represents reflection in the origin or reflection through origin, or this describes the reflection of a point pxy about origin or through origin. So notice how it is coming from, diagonal elements are changing from 1, -1, 1, -1 to -1, 1, and finally to -1, -1. So we have come from reflection through x-axis to y-axis through origin. We'll see two more reflections. So one is reflection in the line y equal to x. So one is reflection in the line y equal to x. For that, we know that if you have got this kind of thing, so you have got a point P that is x comma y, and this is P prime is x prime y prime. So reflection becomes this in the y equal to x line, that is x prime is y and y prime is x. So x prime is y means I can write this as 0 into x plus 1 into y. This is 1 into x plus 0 into y. And so the matrix T, let's write x prime y prime also, equals, that's here 0, 0 and 1 here, and x comma y. So we say that the matrix T equal to 0, 0, 1, 1, this matrix 1, 1. So that matrix is this is a reflection. This represents reflection in the line, y equal to x. So that is the reflection in the line y equal to x. Next we have reflection in the line y equal to x tan theta. So we have reflection in the line y equal to x tan theta, means that we have got some line that makes an angle theta. It may be negative or something, that does not matter. This is pxy, and then we want reflection about this line, that is p prime x prime y prime. Now in coordinate geometry we have got this relation, that how to find reflection in the line. So I will write this line and find it here. Y is x tan theta, I can write as y is x sine theta upon cos theta. So I can write here x sine theta minus y cos theta is 0 is the line, and this is p point xy. I want reflection is x prime y prime. So there is a result that says reflection is x prime minus x, y prime minus y. And then what we are doing is that we are just writing this line xy. So for the sake of brevity, we can better write that as this is capital X and capital Y, so that we don't have any confusion here. So it is capital X. So this is x prime minus x, and you put xy here. So that is x sine theta and minus y cos theta. So I can write x sine theta minus y cos theta. So, and then y prime minus y. And then here, let me just write this in a different matter. So, or let me write the result first so that you can understand quickly what I'm referring to. So I'm referring to this way, changing notation a little bit. Alpha beta is there. And suppose here PQ is the reflection in the line AX plus BY plus C equal to 0. Then I can write this as P minus alpha. So reflection is P, so P minus alpha upon A, Q minus beta upon B, means this is reflection, and negative of, I can write here A alpha plus B beta plus C, and upon I can again write this as A square plus B square, that we can derive easily. And so this becomes your formula, that reflection of alpha beta in this line is given by P minus alpha upon A, Q minus beta upon B, and negative of A alpha plus B beta plus C upon A square plus B squared. Applying this one, if we do this, we will get here x prime minus x, y prime minus y, and upon here sine theta, this is cos theta, is negative of, and so let me create some space and let me write it here. Okay, so let me write it here. So equal to, this is equal to negative of, and here it is cos squared sin squared is 1, and here it is same thing that you have done, that x sine theta and minus y cos theta. If you do this, then this is 2 times will come, because the reflection is also negative 2. If you do it, then ultimately we can change sine square theta to cos 2 theta, and then x prime and y prime turn out to be, x prime is x times cos 2 theta plus y times sine 2 theta, and y prime is x sine 2 theta minus y cos 2 theta. That's the standard derivation. And the moment you get this, then you can write that x prime y prime, that equals cos 2 theta sine 2 theta, and then sine 2 theta negative of cos 2 theta, and this is x and y. This was, so this matrix, the matrix that you got T, that T equal to cos 2 theta and sine 2 theta and sine 2 theta and negative of cos 2 theta, this matrix represents, so that represents the reflection. So it's a reflection matrix. It represents reflection in the line y equal to x tan theta. IIT gives you sometimes some problems based on this, that what is the reflection of this point in this one. So if you know the matrix, you can simply multiply and you can quickly find the result. So that is reflection in the y equal to tan theta. The last one we will do is rotation through an angle theta about origin. This we will do in the last one. That tells you this diagram, that you have got this kind of thing, that is your P x comma y. It might make some angle with some phi axis phi. Now you're rotating it through an angle theta, means that this arc goes like this, and this becomes P prime, and this P prime only is x prime y prime. So your OP equals OP prime is R. It's like you have just rotated this point, some point through some angle theta. So it goes like this. This P reaches P prime. You want coordinates of P prime. Angle is theta degree anti-clockwise. This is theta, and this is theta anti-clockwise. So theta anti-clockwise, which is clockwise, you can take to be negative. So theta anti-clockwise. In this case, we will get again x prime y prime. So we'll get this x prime as x times cos theta minus y times sine theta, and y prime again standard result, x sine theta plus y cos theta. And in matrix notation, I can write this as x prime y prime, that equals here cos theta minus sine theta and sine theta and cos theta, and times this is xy. So once I write that, then I say that this matrix T, that is given by cos theta minus sine theta cos theta, this matrix represents, so this represents rotation by an angle theta, anti-clockwise. So this is anti-clockwise and through origin, anti-clockwise and of a point anticlockwise of a point on a line through origin. Means we have just got one line, this line, and then you are writing that okay, this point moves about. So there is a point here P which makes this one, and rotate this point P about origin. So this means about origin, join up O to P and rotate OP, and it reaches somewhere. So that is called reflection of a point about origin through an angle theta. So you got this matrix A. Now notice two things. So in all of them, wherever you have got reflection matrix, we know that orthogonal matrix is orthogonal definition is M transpose M equal to I. And so we get det of M either -1 or -1. Okay. What is the geometrical significance of it? This is algebraically that det M 1 and -1. Geometrically, what happens that if you have got rotation matrix, so for rotation matrix, your determinant at both are orthogonal. So for rotation matrix, determinant happens to be 1, as you can see here also. And for all reflection matrices, if it is a reflection matrix, then det happens to be -1. So see, we had got these matrices. First was reflection through x-axis. If you remember reflection through x-axis, that we started this with this only. Reflection in the x-axis, that was this one, 1 -1 0 0. Then y-axis. So we got reflection in the x-axis, that was here 1 and -1. So that is 1 and -1 and 0 and 0, reflection in the x-axis. Then reflection in y-axis, that was given to be -1 1 and 0 0. Reflection in x-axis is reflection in x-axis, this was y-axis. Then reflection through origin, so through origin, then you got here -1 and we got -1 0 0. And reflection in the line y equal to x, so y equal to x line reflection, that reflection was again given by 1 1 and 0 0, that is this. And then again reflection in the line y equal to x tan theta, so that reflection was, that relation was that cos 2 theta, this was cos 2 theta, negative of cos 2 theta, this is sine 2 theta, and this is again sine 2 theta. That is reflection in the line y equal to x tan theta. And rotation about origin through an angle theta, that was given by a different matrix, and that was given by, of course, this was cos theta and then cos theta and negative sine theta. Watch out for this negative here, and sine theta. You find that is, if you calculate determinant of each of them, so this determinant value, if you come here, it is -1, here -1, this determinant is 1, this determinant is this one, and this determinant you are writing, this is again -1, this determinant is again -1, and this determinant is this determinant that you are seeing here, this is again, this is +1. And so you are seeing that rotation has got a different thing. So we can conclude that reflection and rotation, they are the basic things that we have done, and we have shown that okay, this is the manner in which things will proceed. So that's what is about geometrical aspect. Next time we will continue with other thing. So let me now stop sharing. Okay, that's all for now today.